Now, one other type of circumstance that we investigated beyond the slant asymptotes, which again we're ignoring, are what are called removable discontinuities. And so if we compare the two functions that are in front of us here, 1 over x minus 1 on the right there, and then a little bit more complicated function on the left. But what we can see here is we can factor that denominator into x plus 1 times x minus 1. And so then we can reduce it so we end up with 1 over x minus 1, which is the exact same function as the second. And so both of these functions, their graphs will look identical to each other. They will both have a vertical asymptote at positive 1. But the difference is f of x has what's called that removable discontinuity, because if I plug negative 1 into this function here, I get 0 over 0 before we did our reducing. But over here, if I plug in negative 1, I just get negative 1/2 as my output. So that one value is a difference between these two functions. And so what we observed at that time when we studied these is that at these removable discontinuities, at these locations where we can cross-cancel away a factor, whatever makes that factor equal 0, at that x value, we would have a hole in the graph. There would be an open circle. So the graph would approach that location, and even just short of it. So in this case, negative 1 being that illegal value, if we plug in negative 1.1 or negative 0.9, the function works just like this one does. But at that one location, at x equals negative 1, we get an undefined value. And so because we're always going back to the original function, not this one that's been reduced after we removed those two factors from the top and the bottom. So we end up with this open circle, this hole in the graph. So the idea behind that y value of the hole, so when we consider what is the y coordinate of the hole were it not there, we say that that y value, that output of the function, is the limit of the function at that particular x value. And so the definition of a limit of a function is described here. It's going to sound like a lot of word salad. So we say that L is the limit of the function. So it's the output of the function as our input x approaches some value c. So trying to translate this, like the output of the function L, the limit, is the value that it approaches as x gets closer and closer to c, to some value. So as x gets closer and closer to negative 1 in the example that we have up above, what is the y coordinate? What is the output that the function is approaching? That's the limit. So in this case, for the example up above, negative 1/2. And so again, you can read through this definition here, but the base thing that you have to take out, the key piece of understanding, is this idea that we're trying to figure out what is the output of the function approaching as the input of the function is approaching some value. So the limit is that y coordinate that the function is approaching as we get closer and closer to some specific input value. So I realize that there's a lot of terminology here and some symbolism with this limit and this x and the arrow approaching 2 that's confusing. But let's see if we can kind of power our way through a few examples to try to clarify some confusion and see what's happening here. So what this first question is saying is, we want to know what is the limit. So what is the y coordinate that this function approaches as x gets closer and closer to 2. Now, our first step in trying to determine this is to just try to plug in that value of 2 into this function. And in this case, there's nothing stopping us from plugging in 2. There's no division by 0, there's no square root of a negative or anything like that that results in plugging in 2 into this function. So I'm going to just do exactly that. I'm going to plug 2 into this function. And so 2 squared is 4, 4 plus 2 times 2 is 4, so 4 plus 4 is 8. So our limit as x approaches 2, as x gets closer and closer to 2, the y value, the output of this function, is getting closer and closer to 8. So that's all we have to do. If we can plug the value into the function, that's just what we do. That's the y value that the function is approaching as we get closer and closer to the particular x value. If we take a look at the second example, right here, same idea. So we want to know what is the output of this function approaching as x gets closer and closer to -2. Well, can I plug -2 into this function? You bet I can. -2 minus 2 up top is -4. -4 divided by -2 squared is 4. So -4 divided by 4 is -1. Again, in this second example, there's nothing stopping me from plugging in my target value of -2 for x. So we do it, we just crunch it out, and so as x gets closer and closer to -2, the y coordinate, the output of this function, is approaching -1. So our graph is just going to go through that location, -2, -1. Or on the previous question, 2, 8. Now in the next one, we clearly cannot plug in our target value of x into this function. So as we look here, we're told that we want to find the limit. We want to find what is the y coordinate that this function approaches as x gets closer and closer to -2. But if I try to plug -2 into this function like I did the target number on each of the previous ones, I get 1 divided by 0. I can't plug that number in. So I have to figure out, I have to kind of piece together what is happening at x equals -2 with this function. I need to decide, is it an asymptote or is it a removable discontinuity? And on this one, it's an asymptote. There's nothing for me to cross-cancel away or anything like that. I just have a very simple rational function, 1 over x plus 2. So if I was to sketch the graph of this guy, I would go to -2 and I would put in a vertical asymptote, and I'd have these two separate branches to the graph, one looking like this and one looking like this. And so what this tells me is, as I get closer and closer to an x value of -2, in this case, my graph just goes haywire. It just goes crazy. On one side, the graph is shooting up to positive infinity. On the other side, my graph is going down to -infinity. And so what that tells me is there is no y coordinate that this function is approaching as x gets closer and closer to -2. My function diverges. It takes off to infinity and -infinity depending on what side you're approaching from. So there is no limit. There is no y coordinate that our graph is approaching as we get closer and closer to an input of -2. But let's contrast that with the second one in this middle row. Now we're still trying to figure out what is the y coordinate as x gets closer and closer to -2. But this time, if I just take -2 and plug it into my function, it still doesn't work like the top two examples, but I get 0 divided by 0. -2 plus 2 is 0. -2 squared is 4 minus 4 is 0. So I get 0 over 0, which tells me that I've got this indeterminate form. We used that term previously, which is the signal that we have a removable discontinuity. And so what we can do here is we can factor the bottom. And so I can cancel out the x plus 2's, and I'm left with 1 over x minus 2. And so now I know that there is a hole in the graph at x equals -2 at this location where I removed the discontinuity. And so it's not a case like the previous example where the graph is going haywire at this x equals -2 location. I just have a hole. And that hole, I can figure out what that y coordinate would be if it didn't have the hole by taking -2 and plugging it into the remaining function. This is the same sort of thing that we did before. We've just started to use this term limit to describe what the y coordinate of the hole is. And so if I plug in -2 into what is left behind after I've done my reducing, I have 1 over -2 minus 2, and so we get -1/4. So negative 1/4 is the limit of this function as x approaches negative 2, meaning that negative 1/4 is the y coordinate that the function is getting closer and closer to, but the moment we plug in negative 2, we end up with a hole at that location. So we're inching towards it. If it wasn't for the fact that we had this removable discontinuity, negative 1/4 would be the output of this function, but it just isn't. For the last set of questions, we've got a little bit of a different circumstance here in that we can see that for our limits, we've got x approaching 0, and then we've got this from the negative side, and then x approaching 0 from the positive side. I'll explain what all this means. And then we've got just x approaching 0. And we have this function, absolute value of x over x, that we're working with. So, of course, if we plug in 0 in for x, we see in all three circumstances we get 0 over 0. It's the same function every time. But what exactly are we going to remove? It's a little bit tricky to comprehend. So let's see if we can kind of unpack this by looking at the graph of this function. So if we plug in positive values for x, if I plug in 1, 2, 3, 10, 1,000, I'm getting 1 over 1, 2 over 2, 3 over 3, 10 over 10. So what I have here is a graph that is just constantly giving me an output of 1. So if I plug in 1/2 for x, 1/2, absolute value of that is 1/2 divided by 1/2, I keep on getting 1. But the moment I get to 0, 0 over 0, something's going on. So the first part of my graph looks like this. I have an output of 1 consistent for any positive number I plug in for x, doesn't matter how big or how small, but at the y-axis I suddenly get this undefined value, this indeterminate value, so I have an open circle at that location. What happens if we plug in negative values for x? Well, if I plug in negative values for x, the numerator turns into a positive because of the absolute values. If I plug in negative 1 or negative 2 or negative 3, I'm going to get 1 or 2 or 3. But the denominator is not going to change. It's still going to be that negative value. But I'm going to be dividing the same number on the top and bottom, just one is positive and the bottom is negative. So that means I'm going to get a series of negative 1s as my outputs. But again, as I tick over to 0, I end up with an indeterminate value at that location. So this is really the graph of our function. This absolute value of x over x looks like this. As long as we plug in a positive number for x, 1 is our output. If we plug in a negative number for x, negative 1 is our output. The one place where things don't work quite right is at x equals 0. Well, so how does that fit with the questions that we have here? So when it says the limit as x approaches 0 from the negative side, that negative sign means that we're just concentrating on the function as we approach the target value from the negative side of the number line, from the negative side of the coordinate plane. So as I inch in closer and closer to 0 from this negative side, what is my y coordinate? Well, it's consistently negative 1. And so it seems like it should continue that way as long as I'm inching closer. I keep on getting negative 1 as an output. So negative 1 is my limit as x approaches 0 from the negative side. However, if I switch to the next question and say, all right, now I want to approach 0 from the positive side, well, what happens? Well, now our outputs are consistently 1, 1, 1, 1 as I get closer and closer. If I plug in 0.1 for x, 0.01 for x, 0.001 for x, I keep on getting 1 as my consistent output. And so my limit, it seems as though the expectation that I have is that the output should stay as 1 even as I tick over to 0 as my x value. Well, here we ended up with two different answers for our limit depending on which side of the target value we were approaching. As we approached x from the, or 0 from the negative side, as we were approaching from the left, we got negative 1 as our limit. As we approached 0 from the right, we got positive 1. So for this last question here, what we're being asked is, what is the overall limit of the function? And for this question to have an answer, it needs to be the same from both sides. If these were both 1, or if these were both -1, then our limit would be just that. It would be whatever that common number is. But because there is not a consistent value between the two different sides, we have no limit. If we go back to the example up here, if we were to look at this graph, if you were to graph this on your calculator or on Desmos or something, we would see that the graph would be approaching this y coordinate, this same point, -1/4 as the y coordinate, from both sides, from the left of -2 and from the right of -2. But in this case here, depending on from which side we approach that x = 0 input, we have two different plausible y values. And so that's why we say that we have no limit in this type of circumstance. So there are times where we will focus in on a limit just from one side or just from the other to determine if the function has a y value that it is approaching or if it is not, as we see in this case.